we'll be using the Try It Online Occam emulator. The bottom URL is the one you want. These URLs are in the comments of the code. The code is in the description, so just go to the description and copy and paste, and you're all set to go. We've seen byte vectors before, so here we have 3 byte vectors of string, which is equivalent to string 0, string 1, and string 2. Well, we can also have channel byte vectors. So 3 channel byte out is the equivalent of out 0, out 1, and out 2. So this allows us to define things under programmable control, which is very convenient when you need to change things every now and again. Take a look at our pipeline, starting out at the brute force and going to a more elegant approach. So this is our brute force pipeline. You need to put something in the input field, so we'll put an A in the input field. And then here's our channel declarations plus the usual in and out. So let's kind of take a quick look at this. We declare byte A, and we input from the keyboard or input field into A, then out 0 bangs A plus 1, so it should be B. Then here we input out 0 from the previous process, increment it by 1, and then bang it out. Now these processes are all identical except for the channel designations. So the channel designations are different, but they're basically all the same. And so finally we get out to the end and we do out. So let's see what happens. So we run it and we get I, because we incremented it 8 times. There's 8 stages. Okay, let's take a look at a slightly more sophisticated way to do this. Okay, this is clearly less code. So here's our kind of generic pipeline stage. Is in gets A, out gets A plus 1. And then we're going to have the same channel, 0 through 6. Remember, we have an in, 0 through 6. And then instead of 7, we're going to use the word output. So that's a total of 8 stages. 0 through 6 plus 7 is 8 stages. So let's kind of, again, take a look at this. We're going to do plus 1 with the parameters in and out 0. So we're going to come up here to plus 1, and this channel will be in and this channel will be out 0. And then we'll send out 0 to out 1, and then we'll call this routine again, but we'll use channel out 0 and out 1, then out 1 and out 2, all the way down to the end where we do out 6. Now we don't really want to use out because that's too close to the array that we define, so we're going to call it output just to make sure that we don't mix up an index versus a non-indexed output variable. So let's go ahead and see what happens when we run this. Okay, we get our same result, but just for the fun of it, let's try a new variable, run it again, and we get J. So that's just, we expect to be 8 stages. So this is far better that it's, you're not repeating the code over and over again. You're just calling the code with different parameters. And this is the real power of formal arguments. You can kind of reuse code over and over again. So let's look at something that's even a little more tricky than this. Okay, so we basically still have our same plus 1. That hasn't changed very much, but the formal arguments are going to be a little different. This time, we're going to declare an array of channel bytes. N is 8, so that's really 7 channel bytes. You always start counting at 0, so that's 0 through 6 channels there, plus we have an input, and at the very end, we're going to have an output, so that's a total of 8. Now, it's important to remember that for all practical purposes, N is a constant for this program. So it's not a variable. I mean, you can change it between programs, but for the run of the program, it's constant. So if you want to figure out what's going on, you can just, everywhere you see N, you can just substitute whatever this is declared. Again, this is literally a variable, a constant definition. So we have parallel. We do our same single step in and out because this isn't called out. We can't use a channel array for that. And then we say I equals 0 for n minus 2 or for 6. We're going to do plus 1p of out I plus 1. But if you remember our previous one, it went 0, 1, 1, 2, 2, 3, 3, 4. So I and I plus 1 exactly the right thing. And then we get down to 6, and then we have output for 7. Again, 0 to 7 is a total of 8. So let's go ahead and run this. But again, we're treating, just like we used to have byte vectors, we have channel vectors. And you can see that, yeah, this maybe isn't such a big savings for 8 stages, but let's see what we can do with this. So let's go back and put our A back and run this. And we get our I back again. So this is actually very pithy, and it's very easy to change. So let's say I wanted to do some huge number of arrays, say 64. I already worked out the math that colon is ASCII 58 plus 64 is 122, which happens to be small z, which actually was the name of my Algebra 2 teacher in high school. What a coincidence that is. Okay, so let's go down here and put in a colon. And then we'll run 64 stages. And we got our small z. So you can see this is very, very powerful. As the number of stages goes up, all we had to do was just change one constant, and instead of doing the whole big writing it out by hand. So for maintainability, this is an excellent way of doing it using the index channel arrays. So we've now replaced the previous one where we used n, and we just put a number in there. And so this is, so the n minus 1, if we have 8 stages, becomes a 7. The n minus 2 becomes a 6. And it all seems pretty sensible. So let's go ahead and run this. And we get I like we did before. So it's a little easier if you're trying to understand it, to actually replace n with an actual number, and then you'll see what's going on. I think the negative numbers always seem kind of confusing to me. But you can see where as you get more and more stages of pipeline, it becomes more and more beneficial to use the channel index array method.